Okay, for real this time. So we're going to do basic stats. So just to start, there's a couple different types of statistics. So we're going to do a very brief non-parametric versus parametric description. Most everything we're going to do in this class is parametric. Descriptives versus inferentials, and then head first into R and descriptives. So parametric stats are used when the dependent variable, so the measure of interest, is either an interval scale. So interval scales are those Likert-based scales where they range from like 1 to 5, where 0 doesn't mean 0. It means it's just a placeholder. So temperature is technically an interval scale because 0 does not mean no temperature. 0 is like what it is outside. Right? So interval scales just don't have a true 0. Ratio scales have a true 0, where 0 means the absence of something. It's a little weird to think about the weight of something to be 0, but in theory it happen. So most of the data we're going to use is ratio or interval scales. Some people just call them scales because that's not confusing. So continuous data. And that requires a lot of assumptions. So the data screening section is we're going to go over all the assumptions and talk about like how you can screen them all at once. And then for each individual statistic test, we're going to talk about what type of data screening you have to do for that one. So we're going to kind of do like big data screening and then apply it to each test. And most of the stats we're going to use are going to be parametric. So ANOVAs, regression, we're going to do factor analysis. So most of the stuff you see is parametric. Non-parametric is when mostly you're dealing with categorical data. You can actually do non-parametric stats on any type of data. It's actually more flexible, but most people don't like it because it's a pain. And so we're going to just stick with those, do log regression and chi-square. And that's where the DV is categorical. So it's like non-parametric's actually better because no matter what your DV, you can use it. But people don't like it because it's hard to interpret. And it used to be hard to run. Now not so much. It doesn't require those assumptions. It has slightly different ones. Non-parametric is like your cool friend that only comes and hangs out every once in a while. It doesn't mind when you break the rules. So just every sort of research idea has two pieces. You have the descriptives of like what happened in the study, or what where the average is, what's the picture of the study, and then you have inferentials. So inferentials is what conclusion can I draw, what happened. So descriptive stats create a picture you describe. These terms aren't so hard. We've got the mean, which is our average of all scores, and variance, which is the average distance from the mean. This room comes marker free. No markers. I know. Where's Jessica? We need her. Anyways, but the variance is an average distance from the scores. So I don't remember that. You're going to be able to see this in the back? No, probably not. Yeah, that's enough. Thank you, though. Good try. I don't need one. We'll wait. I'll remember. I'll add that to my list of crap to haul over from Hill. Okay, so variance is the average distance from the mean. So if you think about, like, when people talk about winning the lottery, the joke is that it's if you were standing at the top deck of one of those really big stadiums, football stadiums. I think Michigan has one of the largest ones. So the very top, you were in the nosebleeds, and somehow you had the strength to throw a quarter on the field. The odds of you winning the lottery is it hitting another quarter that happens to be on the field. And so if we take that quarter as our mean of things, variance is how far away are all the people who are throwing these quarters. Okay. So it's an average distance of scores away from the center of the field, or the center of your data. Variance is kind of a pain, though, because it is squared. We're not going to do a whole lot of formulas because on the formulas. But the problem with using variance is that it's a squared distance, okay, for lots of mathematical reasons. And that's hard to interpret. So instead, we're going to use standard deviation. So standard deviation is a standardized variance. So it's still the average distance from the mean, but it's not squared anymore, so you unsquare it. take this very. Also going to use standard error. Standard error is the standardized standard deviation. So think about this. Variance is variance. You have standardized variance, the standard deviation, and they have standardized variance. Yeah, I know. So what's the difference between the two? Standard deviation is a better descriptor of the sample. So I have this group of people, and I'm trying to describe how far they are away from the mean. Standard error is a better description of the population. So yeah, I have this sample, but we're really trying to describe this other bigger group of people, and so we have to account for N here. So N is the number of people in the study, and so I always think about standard error as the Oprah of standard deviation. I think in another set of notes I have a picture of this, but like standard error is like you get some standard deviation and you get some standard deviation. Yeah. That joke will only last for like another couple years. Since she's quit doing her thing. So you're divvying up the standard deviation based on sample size. And so that's supposed to be a better estimate of the standard deviation in the population, those people that you haven't sampled. So because of that, standard deviation is always larger than standard error, because you're dividing it by another number. Which one should you use? Meh, doesn't matter. As long as you tell people which one you're using. Okay, so you can use SD for standard deviation or SE for standard error. And I don't care. So those are the basic things that you might report in a research paper. But I don't think we're going to do a lot of, like, you'll be sick of histograms by the end of the year, is making histograms of frequency tables. So frequency tables show each individual data point. So if I have a data set and I'm looking at the frequency of something, it just tells me there's 6 sevens, there's 8 tens. And that's really useful for categorical data. So you're trying to determine how many people were in each group. A frequency table is fantastic. And that'll be really helpful when we get to brain fart, log regression. Because I want to make sure I have enough people in each category to really try and predict their categories. The frequency table is really simplistic, but it has its uses on the data screening kind of end. But a histogram is even better. So a histogram is a picture of that frequency table. And so people make histograms of continuous data. So why two things that tell you exactly the same thing? Frequency tables are for categorical data, really, and I'll show you an example of why in a minute. Histograms are more for continuous data. So it makes you a picture. All right. Now I really do need graphs. I will try and draw. Y'all, this is going to be great. Get excited. All right. I'm terrible at this, I will warn you. Okay. So with a histogram, what's going to happen is you are going to have that thing where you click the button and it gives you the pin. Oh, you have to be in the other view, don't you? No. How do I do that? View, pin, 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 pin. You guys really, I prepared this last night. Tools, pin, pin. Whatever, okay. So, nope, you lied to me. I heard that off the top. Shape. There we go. We're not. PowerPoint hates me today. There we go. All right, so we got Y. All right. Got X. So everything along the bottom here is going to be, in a histogram, is values. So these are the actual values of the data, and this over here is the frequency of the data. So if my scale, let's say we're talking about quiz scores, ranges from 0 to 100, that would be what the values are on the bottom. So it's always low end on the left, high end on the right. And then the frequency of each score over here on left. And let me back up a second. So there are a couple of types of distributions that you can have. So you can have unimodal distributions, they have 1 hump. Bimodal distributions, 2 humps. Multimodal, 3 or more. I was doing this exact part of this lecture this morning, and I was just like, really, this isn't hard. Okay, so unimodal distributions just have 1 mode. Bimodal distributions have 2 or more, or 2. Multi have 3. A rectangular distribution makes a rectangle. So I think I can do one of these things like, ooh, no. Maybe I can manipulate it? Nope. I will just Google it. Okay. So, unimodal histograms have 1 hump. Okay. Ta-da! Look how pretty it is. Multimodal histograms have more than 2. Right, 3 here. Oh, here's a great one. And bimodal has 2. So they don't have to be perfectly even. Right, so a lot of books say it has to be a perfect mode. I'm like, that's the stupidest thing I've ever heard. So if it looks like it's got 2 sets of histograms kind of next to each other, it's bimodal. Uniform or rectangular is straight. Okay, depends on which book. I've always called them rectangles because they make rectangles. That makes much more sense. Okay, or multimodal where it has a couple of humps. Thank you, Internet. My drawing skills are bad. Very specifically, there's one called the normal distribution. This makes me crazy because it's the least likely thing you're going to get. Let's see if we can get a normal one. Where's that normal paranormal joke? Because it makes me laugh. I don't know if y'all have seen this one before. Yeah. He's so cute. This always comes up at Halloween. I'm like, that's never not funny. I don't know what it is. Normal distributions are unimodal and symmetric. So you can fold them in half, hot dog style, and they are even on each side, and they're unimodal, one hump. Okay. They have their advantages, and we're going to actually assume that a lot of things are normal that actually aren't. And then when we get to data screening, we'll talk more about like why the normal thing, and talk about, there's this really cute video called Distribution Bunnies that I'll put online for you guys to watch. And they're laughing because they've seen it. It's about why the normal distribution. Okay. But we're going to use it. And there's that one. Oops, this way. So to describe distributions that aren't normal, there's 2 descriptors, skew and kurtosis. So skew is how much it leans from normal. So think about this like politics, right? So how far do they lean left or the right? So if we had a Trump distribution, it would just basically be all the way to the right. There would be nothing on the left. At the moment, anyway. See what he does next week. So skew is how much it leans. This kills people. This term right here, this is things that people missed on the test, the quiz, that should be very easy, but it's not what you would think. Okay. So a negatively skewed distribution there we go. Here's a good picture. Actually has most of the data on the positive end. So the way to think about this is if you draw a little kitty cat head here, the skew is where the tail is. So it's called skew because it's where is the data that's causing the skew. So if I lop off the tail, it becomes a normal distribution. So the tail is the problem, so it's where the data isn't. So this is a negative skew. I think it's just because you would expect this to be positive because it leans to the positive side. It's backwards. Okay, so negative skew has more data on the positive end and none on the low end. Positive skew, more data on the bottom, not enough data on the top. Okay, that's where the data is missing. I always draw, like, I saw this in an intro book once where there's a little kitty cat head on it, and it's wherever the tail is. So a negative skew is sometimes called a ceiling effect. That's where everybody gets everything right. Positive skew, floor effect, where everybody gets everything wrong. Kurtosis is a completely different animal. So you can have skewed distributions that are kurtotic and kurtotic distributions that aren't skewed. So you have to treat these things separately, but they can overlap at the same time. So skewed distributions also tend to have kurtosis problems. But that's how different it is in shape. So how much skinnier than normal and how much fatter than normal. There's a really famous picture for this. I don't care if you remember the terms. Okay, where is my, there it is. Okay, so a leptokurtic distribution, like I said, you don't have to know this, is the kangaroo one. Because it has really long tails. A platykurtic distribution is the platypus one. So platykurtic distributions are very flat, like a platypus. Leptokurtic distributions are very skinny. You're more likely to have the leptokurtic problem. And the way I remember leptokurtic is that you have to leap over it, it's so tall. But I mean, once you get the idea that kurtosis is like how different from normal it is. Okay, so here's another one. And then mesokurtic is normal, but that just seems silly because that's hard to spell. Right. So here's another one. But kurtosis is a problem when you have too many people in one area. So if you ever have done like one of those 1 to 5 scales that everybody picked 4 and 5, that's a kurtosis problem. It's not a skew problem. If you have everybody pick 4 and 5 and then 1 or 2 ones, now you've got both problems. So you can have both of them at once. Or neither. It could be normal, which doesn't happen very often. Usually when somebody shows me a normal distribution, I'm like, what did you do? I think we had that conversation in the lab one day. I remember who it was, but I was like, how did you get that? So let's try it. Frequency tables, histograms, and a bunch of other stuff. Let me do this. Okay, so can I squish it and it still be readable? No. I had all this open when I was testing it. 1 second. Okay, so that should be big enough for people in the back, yes?
Can you make it a little bit bigger?
This? Yeah, okay. I can, but we're going to be bordering on crazy windows here in a second. Alright. So first thing we're going to try is a frequency table. Okay. And on all of this, I tried not to go too heavy on the descriptors because I'm going to give you an assignment where you can try a lot of this. One thing I'm trying to do, and I may or may not remember for the rest of the semester, is if it's in italics in here, that means that you have to fill that in with something. If it's not in italics, those words have to stay. Okay. So we spent last week talking about you got to do column names and not just variable names. So that's the $sign operator stuff. So what we're going to do is load some data. So you want to down all of this. Just like it's vodka, right? Okay. Download the data sets from Blackboard. Let's try again. There's a bunch. Sorry. Okay. So I included a bunch of data for us to use. Stick them somewhere where you know where they're at, in a folder somewhere on your computer. And we're going to start importing data. That was the very last thing on the assignment, so we're going to practice that now. On all of this, don't get lost and don't let yourself get 3 steps behind. Just say, yo, what? I don't understand. I will not react poorly, I promise. Unless you ask me what the check mark thing is. I had a student ask me that one time in another class. Check mark symbol. Anybody? The square root symbol?
Oh.
I was like, I couldn't control. I'm usually pretty good at controlling my face, but I was like, what? Well, what is that? Oh, it's a square root symbol. Well, how do you do that? I'm like, you hit the check mark button on your calculator. Like I can. So, but everything else is fair game. So let's import the basics data set. So I'll click import data set. from text file, wherever you hit it on your computer, which for me is like 8 folders later. I know, don't judge me. I like folders and folders. So you should get to this window. Like that. I don't even know. I don't. Okay, we'll figure it out. So we'll use air quality. So every semester is something new. We'll see. So let's make a frequency table. Yes. So the code is simply table. Okay. You do have to tell it what data set it's in, so we're going to just air quality it. A $sign thing to tell them which column you want. And temp is not a bad column, because it'll give you an example of why frequency tables are not very good for continuous data. So I'm going to do Command Enter or Control Enter to run it. So it gives me a table. Okay. They are not pretty, but the first row on each sort of block is the actual data. So temperature includes scores from 56 to 97. So they're doing this in the south, clearly not here. Okay. And then these numbers here are the frequency. So there are 3 days that are 57 degrees, and 81 is the most frequent, 11 days. But that sort of table is not very good for continuous data. So let's look at some, non-continuous data. So I'm going to do air quality, and then pick month. So it has month coded as an integer, but clearly that's not really a number. And so that looks much better. The frequency tables are much better for small data. So things that have very restricted ranges, like your Likert scales, 1, 2, 3, 4, or categorical data. Okay, so month is clearly a categorical kind of thing. So there are several ways to make histograms. This is the simplest. So we're just going to do histogram. It's your column name. And this bin width thing allows you to control how wide the bars are on the histogram. So we're going to try a couple different numbers here. So it's just hist. Hist for histogram. There's another function called histogram, but it's hidden in a package you don't always have open. So use hist. So it's air quality. Let's do temperature again. And I'm going to leave off bin width for a second. Okay, that's the real problem. What is that? So, look how normal it is. This is because it's made up data. But this is the automatic sort of version it gives you. So it tells you that it's temperature, and then it tells you its frequency over here. But what if we didn't want the bars that big? What you can do is say comma here. So this is 2 arguments. So they both go inside the parentheses. Do bin width equals and pick a number. Let's go 5. Bin width. Did I spell it wrong? Bin width is not a bin. Listen, you. I literally did this in my last class with the same data set. Or is it bins? No.
This is the air quality data set,
No,
not ours.
literally, I did this on air quality with him. It's not a graphical parameter. Why are you haterating on me?
About using breaks.
Breaks!
That's what we use. Yeah.
I said it doesn't look familiar.
Thank you. I'm so proud that the front row remembers something from last semester.
Front row be John.
It's, breaks.
I just knew it didn't look right.
Bin width is in ggplot. Sorry. Bin width is in a package we're going to use on another day. So it's breaks. There we go. Breaks, not bin width. So what that did is it should have squished up our plot some. It did not. Did nothing. Mine look different. If you flip back and forth between them. Here, under plots. Shwink, shwink, shwink. Okay, try making one with 50 as breaks. And that should really change.
Look at that.
Yes? No? You guys. Yeah.
1 million breaks. Just gonna start adding.
It may look slightly different because of the rendering.
Okay, it works.
Okay.
It does not like that.
Okay. 1 million. 10 is not a bad number. 10 actually might give you the exact same plot. 5 is not a bad number. Just gonna get little tiny lines. So what does that command do? It changes how much is in each bar. So it changes how it's grabbing each little bar. On the what? Right. So if I make breaks really small, that means it can only have that many in each bar. So the frequency on the side is going to change accordingly. If you make breaks really big, it's going to, I think I said that backwards, but it's going to change how tall it can be. That makes sense? Yeah. So it's actually changing the bars, but that changes the side. Don't say that. Okay.
You put a million breaks.
I tried to do a million breaks, and now I just want to do it again.
Oh. So, that's no good. Okay, let's see if we can get through descriptives. And then we'll take a mental break. So let's do the mean function. So there's 2 functions for mean, and they're useful in different times, and we're going to use both of them for data screening. So we're just going to talk about both. Okay. So the summary function is one of my favorite things about R because it does either averages or tables depending on what type of data you give it. So summary is kind of a smart function. It figures out what the data you're putting into it is and then spits out the right output. Okay, so we're going to use summary a lot. But the cool thing is summary will work on an entire data frame. So I don't have to tell it which column. So this is going to give me every column at once, which is not so useful if you have 900 columns. But if you have a couple, it's not a big deal. So if you run that summary function, so it'll give you the minimum. So min here is minimum. Max is maximum. Yeah, that's not too bad. First and third quartiles. So it breaks the data into 4s. The median is the 50th percentile, but the most important one is the mean here. So I can tell what's the average score for each column. Okay. Now for month and day, that's not very helpful, but it went ahead and gave it to me. And then also here, this NAs thing. It'll tell me how many missing values I have for each column. So that's the summary function. Other way to do this is to use the mean function. Now this one you do have to do one column at a time. So I'm going to do air quality, and then temp. But I have one more little piece here. So this na.rm, what that means is that do I remove the missing values? If you have missing values in a column and you ask it to calculate a statistic, it just spits an NA back out at you because that's helpful. And the default is for it to be false, also not helpful. So in a perfect world, this would be listed as true. It is not. So you have to remember to tell it to be true. So you would type na.rm equals t for true, or you can type the word true. It'll turn blue when you do it. And don't change anything about that. So that just basically says exclude any missing values. And that's going to be helpful if you ever it spits an NA back out at you. It's usually because you have missing data and it doesn't know what to do. And NA.rm is the most common way to deal with it. Let's run that. It tells us the mean of temperature is 77.88, which will match up here. So the summary function automatically ignores NAs. All right, so then...
Can you always just write T instead of writing untrue?
Yes. Like half of their semester was like, really? Yes. You can write T and F for true and false, or you can spell them out completely.
And it only turns blue if it's something it will run.
Yes. It's a reserved word.
Okay.
Like you can't call a variable T. We'll get mad at you. Well, you can, and then it gets mad at you.
Yeah.
So to calculate variance, same idea. Var, column name, NA.rm equals true. So what I could do is just copy this line I just typed. And then just change the function to variance. Okay. Often when you sort of like stop and hover, it'll give you some descriptors. That's the help file. So it's kind of telling you, like, here's the things you should type. We aren't always going to use everything. So we don't have a Y. Okay, we're just going to do X. What kind of shows you? What's going on? Go away. Okay. So the variance for temperature is 89 points. Does that make any sense? If the average is 78 points, and the average distance is, squared distance is 90 points, like, that's like in temperatures that are in volcanoes. So we don't really tend to use variance because it's not a helpful number because it's squared. So it's 89 squared points away from the mean, and people just look at you and go, what? So instead, standard deviation. It's the exact same code, but SD for standard deviation, which is better than the code for Excel, which is STD. Every time I type it, I'm like, why? Who programmed this one? All right. So 9 points makes a lot more sense. So on average, the mean of this magical place is 78 degrees, and it varies about 9 points. And that makes sense. So 78 plus 9, 78 minus 9, that's the normal range of temperature. So you can kind of think of standard deviation as like, what is a normal range of the data? Okay. Anything past 2 standard deviations is usually considered abnormal. Now the problem comes in when you're trying to calculate standard error. There's not an SE function. There is one in another package, but it's not worth the trouble. So what we're going to do is take the formula, I can make it a little bigger, for standard error, which is standard deviation divided by the square root of n, and get n automatically. So I could look at the environment window over here and see that there's 153 people and type that in. But we're going to try to avoid doing that all semester, because then if you make a change to the data, you're stuck with remembering to change that number. Okay, so we're going to try not to hard code anything. So I'm going to take my standard deviation, so this exact line I just typed, and divide by the length of that column. Okay, so the length function tells you how many things there are, but in this column. So air quality for temp. But then the formula, yes? Yes? Okay. The formula is that's actually the square root of that. So I'm going to put square root around the length. So it's SQRT. Okay, so it should look like, take the square root of the length. So we can do functions and functions. Your funception, I guess. We really have lots of functions and functions, so this is probably one of the simplest ones we'll do. Okay. So it's take the standard deviation, divide by the length, and that'll give me a standard error, right, of, 0.77. So that's 9 points divided by the square root of 153. So that's how I can get my basic descriptive stats. So how do I get skew and kurtosis? So let's see if this column is skewed. So temperature is pretty normal. So let's see how normal it is. We're going to have to install the moments package. I already have that on my computer, but you would click packages, install, that's moments. So let that bad boy install, do something, there it goes. And if you already have it on your computer and you install it again, it just overwrites it, it's not a big deal. I'm going to load the moments library because if I try to use it, nothing will happen. I'm going to, there we go, type up here. So library, then moments. Or you can click on it over here. And the code is a variation on the theme of what we've just been doing. So you can actually get it to give you the entire data frame at once. I don't recommend that because if you include categorical variables, it barfs. So sometimes it'll lock up if you do that. So what we're going to do is basically do this again. But the code is skewness, not just skew, skewness. But you see how it's the same code over and over again. All we've really been doing is changing, okay, it's mean to var to SD to skewness. So it's a similar pattern of code. So the skew for temperature, which we had made a picture of, is slightly negative. 0 is a perfectly normal distribution. So it's slightly negative because there's slightly more data on this end. And then we would do the exact same thing, which I feel like I've said 100 times today, except it's kurtosis. I'm glad it's not kurtosis-ness because that would be awkward. So the kurtosis is 2.57. Where'd my little plot go? There it is. Okay. And that's actually pretty high. So a positive kurtosis means it's squished up. It's lethargic. And so because these are so much taller than these other ones, it's a skinny distribution. A 3 would be bad, so we're close to bad. 0 means it's perfectly normal.
So 3 is getting close to like a maximum limit.
Oh no, skewness can be like 6,000, but 3 is like where we start to worry. That's too skinny, or -3 would be too flat. And we'll talk about that more in data screening. So I can calculate actual numbers for skew and kurtosis instead of just looking at a graph and like in reading tea leaves. Because a lot of the data screening will feel like, we're going to make a Harry Potter reference. What is it? Trelawney? Is that how you say it? Thank you. Like her reading tea leaves in a cup is data screening. Get excited. All right.
Sorry, you want skewness and kurtosis less than 3?
Yes.
Okay.
3 positive or negative. Yeah. It's a z-score.
Okay.
So a little bit on inferential. So most of this is actually just going to be talk. Yeah. I lost where I was. Sorry. Hold on. Too far. Okay. So you won't probably need R. You definitely won't need R anymore for the rest of the class. We're just going to do terms. So inferential stats is how we can infer things about the data. So this is drawing conclusions part. So this is the story you're trying to sell to somebody. Generally, an inferential is a question about if something is different from a known data set, is different from some other piece of the data, if they're related to each other. So this is where we get into hypothesis testing. And so I have a bunch of like basic terms for this, and I will try to make it as goofy as possible. And I do this in a sports way, especially to the back of the room. So, hypothesis testing, in a nutshell, is Rock'em Sock'em Robots. So, and that's in the slide somewhere. You have two kind of rival hypotheses going on. Usually a null, that nothing happened, and the study was a waste of time, and a research. So you can think of your research as your favorite team, and then the null hypothesis being your enemy team. Okay? And so you want one hypothesis to win. Okay? And when you win, it's called rejecting the null, or once you get past intro stats, statistically significant. That's what people say. So the null hypothesis is that nothing happened. Okay? So hence the null part, 0. So there's no difference between groups. That's the kind of t-test ANOVA family of hypothesis, or there's no relationship between variables. That's regressions and chi-square. So it's sort of two ways it could go. And that's not what you want to have happen. So you want something to have happened, otherwise why are you doing this study? But you have to say, well, nothing could happen. And then the other option is a research sometimes called an alternative hypothesis, where you expect to find groups are different, there's a relationship between the variables, okay, and there's my Rock'em Sock'em Robots. So you pit them against each other, but only one robot can fall, so you can either reject the null or not reject the null. Okay? And that's why it's called null hypothesis testing. So pretty much everything I'm going to teach you until we get to EFA is called null hypothesis significance testing, because we're testing if the null was rejected or not rejected. So you have this research hypothesis, this idea, but you never actually test it. I know, it's terrible. So there are a lot of problems within HST, but it's kind of what everybody does. So when we walk through each type, we'll talk about the problems with them. But essentially, we've got two hypotheses, and we want to ditch one of them. So how can I determine which one won, essentially? And the most common way is a p-value. So p-values are probabilities of the likelihood of the null robot, never of the research robot. You can also do cutoff scores, which are p-values friendly cousins. And then when we get to factor analysis, we'll talk about fit indices. 90% of the semester is going to be all about p-values. Which, yes, you can laugh. It makes me laugh. Like, there's so many of these terms that I'm just like, who, why, what? Yeah. So we want to reject the null, or say that it's statistically significant, and that's when your team is going to win. And so with p-values, what happens is you want to find the probability of the null is very low. So all the probabilities we talked about is the likelihood of getting this result if the null were true, which is kind of a hot mess, but that's what it actually means. Okay? So people find this odd because you want they think, I want probability to be really high, like the lottery. Like you prefer the probability of you winning to be much higher. Right? But in reality, what we want is the probability of us being wrong to be very low. So we want to reject the idea that our team would never win, essentially. Okay, so we want the probability of them never winning to be very small. Okay. Which, I guess if you were a Chiefs fan at the beginning of the year, was a bit hard to swallow. And then that last game, folks, shot themselves in the foot. Okay. I love football. I'm very sad it's ending. I'm like, how many more days till baseball? Okay. So if I retain the null, or I say it's not statistically significant, that's usually when you're sad. And so you're saying the probability of the null is not low enough, so it could be, our research could be supported, but we didn't find it in the study, so they could be the same, they could be different, but I don't know. So when you retain the null, or do not reject, or it's not significant, whatever term you like, you're not saying that the research is false. You're just saying that you didn't see it in this case. So it's kind of like Sherlock Holmes in a sense of like you never actually say that the research is not true. You just say, well, we didn't see it. Or the way politics work. Right? So they never actually say that something is not true. Like, well, it's just not supported. So the way we determine that is going to be p-values. And this phrasing you'll want to be sure you study. So it's the probability of getting these results from the study, from the t-test, the f, the chi-square, whatever you're doing, if the null were true. So it's the likelihood of finding these results, or crazier, if there were nothing going on. So we want the null to be false, so we want these probabilities to be very small. So industry standard is 5%. So if you've seen p less than 0.05, we've decided that's the magic number that we like. Somebody did. A dude did somewhere along the line. And so that leads us into some decision-making theory. If I'm thinking my slides right, yeah. So alpha is the probability of a type 1 error, which I have on the next slide. And so what happens is, like, we're making a decision. We're either rejecting the null or we're not rejecting the null. So we could make a mistake. So these mistakes have names. So alpha is the main one. It's a probability of a type 1 error, which is rejecting the null when you shouldn't. And I should have it here. There we go. But I just want to make sure it's clear that alpha and p are different things. People get them conflated. So alpha is a value you set. So we've actually decided that in psych, 5% is a good value. So we want things to be less than p 0.05 or p less than 0.01. But it is not the same thing as the actual p from your study. So we might find that the probability in our study is 0.02. That's less than 0.05, so we would say it's significant. But alpha is 0.05. P in this study was 0.02. Okay, so keep these things separate. So we're going to set alpha. So what the hell is alpha? And that's a type 1 error. These are labeled like with the most unfortunate names because they're not mnemonic at all. So the one I remember is that the first mistake of type 1 is the worst mistake. Okay? So it's saying something happened when it didn't, which is like a wildly appropriate right now, the whole making a murderer thing everybody's going nuts about. But that idea of like saying something happened and it didn't, so other people are going to base their research on it. So all of that autism vaccine research that's just crap because that guy, the original study is totally made up. Okay? So he rejected the null, but he actually just made the whole thing up. But that's a different issue altogether. That's ethics. You can reject the null when it's false and just because your study was weird. So things happen sometimes and it's a type 1 error. Now, how would you know that that happened? Well, ethics detection is actually a really interesting form of psych. But generally you don't know. And the issue becomes people can't replicate your stuff. But then there are the times when people actually cheated. That's a different thing. So the first mistake is the worst mistake, saying something happened and it didn't. People go to science jail. Okay. I guess you can't get another job ever. Oh, I don't know. There's several, like, what is it? Zimbardo? Y'all know the famous Zimbardo prison stuff? He's, like, famous and, like, sells books and stuff for being basically a really bad scientist. So, you know, if you work at Stanford, I guess you can get away with it. Every time I'm like, how did he not get fired? How? How did he become super famous and not get fired? I would have gotten fired.
They approved it.
Yeah. Well, IRB was like in its fledgling stages then, I think so. They're like, yeah, sure, torture these people, whatever. You're paying them, it'll be fine. Yeah. IRB now, like, we have one study that has, like, a question about suicidality on it. Like, I think suicide is the way out. That one question we have to do all this crap for, so, you know, they're better now. Okay, the opposite side of that, let me get through these. I think it's beta and then power, and then assumptions. Perfect. We'll do, like, 3 more slides. So, beta is the probability of a type 2 error. And type 2 is when you miss it. So, type 2 is like the battleship. Okay. So, you fail to reject the null when you should. Your research hypothesis is probably true, but you missed it. Okay. And so this is when your team fails to win the game, but they really should have won. Power is when you reject the null and you should have. So this is the perfect scenario. my study is likely, my research hypothesis is likely true, and I found it. So yay, this is publications. We're going to use a little program called G-Power to calculate power. It is free. It should work on everybody's computer. But instead of calculating power, like the likelihood of us finding it, and we should, instead we're going to like rig the system and use power to find how many people we need to find it if we should. So power is actually normally used for sample size calculation. So how many people do I need to find it? Okay. So in that sense, I guess also very relevant, because didn't they call off the search for those guys, Marines that are crashed over Hawaii? Am I talking to like faces? Yeah, BuzzFeed. It was on BuzzFeed, so I know like it was a thing.
I'm surprised I missed that.
Anyway, there was a search going on for some missing soldiers of some type. So power, in a sense, could be how many people do we need to find them? Oh yeah, no, the local news is terrible. All right. This one more slide, and then we'll see if we can solve some of your problems with importing data sets. Okay. So last but not least, so assumptions in your data. So type 1, type 2, power, and beta all go together. Assumptions are things that have to be true for your statistical test to return an answer that is not garbage. Okay. So if I want to believe that your stats are correct, these assumptions have to be met. Okay. So when assumptions aren't met, the answer that you get, you don't know what it means. And there's a lot of bending assumptions because they're very robust. Yes, it makes me think of boobs too. So assumptions tend to be very robust to violations, which means you can bend them and they're no big deal. But we are going to talk a lot about assumptions when we do data screening. Okay. So we're going to end at effect size. Now we'll remember that we finished at effect size, and we're going to solve whatever the hell is going on with your import issues.